All right, we can now actually see a proof sketch of how the fundamental theorem of algebra can be, sorry, not the fundamental theorem of algebra, how the n-roots theorem can be proven. The fundamental theorem of algebra, like I said, requires some pretty advanced, beefy mathematics. We won't be able to see it here, but we can actually understand how the n-roots theorem is being built out of the fundamental theorem of algebra. So, starting with the fundamental theorem of algebra, which we will not be able to prove, and the division algorithm, which we addressed earlier when we talked about polynomial division. The proof is within our grasp. So start off by considering some polynomial p of x with degree n greater than 0. Now, the fundamental theorem of algebra, remember that said that there is at least one root. So by the fundamental theorem of algebra, we're guaranteed there's at least one root. So let's give that one root that we're absolutely guaranteed, we'll give it a name and we'll call it z1 because it's our first root. And we know that p of z1 equals 0, right? It's a root because if we plug z1 in, we get 0 out of the polynomial. So there's going to be at least one root to our polynomial p, and we'll call it z1. Now, from earlier work, we know that if we've got a root, that's the same thing as saying if there's some root that is, causes our polynomial to go to 0, that's the same thing as saying that there is a factor x minus z1 somewhere inside of our polynomial. So by the division algorithm, we know that there exists some polynomial q1, right? We'll just call it q for quotient, and then we'll need to give it a number because there's going to be a bunch of these quotients coming up soon. So we'll call it q1 of x because it's the first time we've divided our initial polynomial, and it's going to be degree n minus 1 because we're going to pull out x minus z1 so that we'll get x minus z1 times q1 of x, right? That we can pull out our factor because we were guaranteed this factor because we know there is a root of z1, so there must be a factor of x minus z1. So we can pull that factor out and we'll be left with that factor times some quotient. So we'll have x minus z1, the factor that we know must be inside because of the fundamental theorem of algebra. And then we pull it out through the division algorithm, and we must be left with some q1 of x. There can't be a remainder because we know that that factor must be cleanly in there. It must be able to divide out evenly, otherwise it couldn't be a factor. So we've got that our initial polynomial is equal to x minus z1 times some other quotient polynomial q1 of x. And since we pulled out a degree of 1 from a polynomial that initially started at n, we started at n and then we pull out 1, we know that we're going to have a degree of n minus 1 in our quotient polynomial. So we can keep going with this procedure, right? We did it once and we pulled out a root and then we broke our polynomial out. We knew that there was a root and then we were able to factor out that linear factor because of that root. So if we have n minus 1 greater than 0, remember, n minus 1 is the degree of our first quotient, we can use the fundamental theorem again, right? The fundamental theorem says as long as your degree is greater than 0, there's a root in there. So if that's the case, we know that there must be some root z2 where when we plug it into our quotient, remember, since n minus 1 is greater than 0, we can use the fundamental theorem of algebra to guarantee that there is a root z2 so that we plug it into our quotient, and so q1 of z2 is equal to 0. Cool. But we also know that z2 has to be a root of p of x because the way that we got q1 of x was by dividing it out. So we have x minus z1 times qx is the same thing as p of x. So if we plug in z2 into p of x, then we're going to have z2 plug in, right, for our x. And so we'll get z2 minus z1. And that's some number. But we're also going to have q1 plugging in the z2 here. So we knew that q1 of z2 equals 0, so that means that the whole thing has to come to 0 because we've got a 0 here, and 0 will knock out whatever else we have. So the whole thing comes to 0, which means that p of z2 has to equal 0. Pretty cool. Now, we can just use the division algorithm again. We know that q1 of z2 equals 0, so it must be the case that x minus z2 is a factor of q1 of x, right? Since it's able to be pulled out, so we can pull out a factor x minus z2 from q1, which gives us, once again, another quotient, our second quotient, so we'll call it q2 of x, and q2 will be a polynomial of degree n minus 2, because remember, q1 started at n minus 1, and then we're going to subtract 1 because we're pulling out a degree of 1. So we subtract 1, so we're going to get n minus 2 as the degree of q2 of x. Now, this means that we can also express p of x as x minus z1 times x minus z2 times q2 of x, right? Since q1 of x equals x minus z2 times q2 of x, and we know that p of x equals x minus z1 q1 of x, we take this right here, and we swap it in for q1 of x right here, and we're going to get this thing right here, x minus z1 times x minus z2 times our quotient 2, our second quotient of x. And we just keep going with this method until eventually the quotient polynomial, until we eventually get down to some qn that's going to just be a constant. We'll be stuck at degree 0. At this point, we'll have a total of n roots because we'll have pulled out one root each time we take a step down, and so we'll take an n steps down. We'll have managed to pull out z1, z2, all the way up until zn. Effectively, what we're doing is we're whittling down the degree of the polynomial we started with. So we're whittling down the degree. For every step we lower the degree by, we manage to get another root. If we start at degree n, that gives us n steps to go down, so we've got n steps to pull from, we manage to get n roots out of it. For example, let's consider if p of x is degree 5. So we start off at degree 5 with p of x, our initial polynomial. By the fundamental theorem of algebra, we're guaranteed that it must have one root, z1 we'll call it. Then we use the division algorithm to break it into q1 of x. Now q1 of x is going to have degree 4, and so by the fundamental theorem of algebra we're guaranteed another root, z2. And since z2 is the root of q1, and q1 is contained inside of our initial polynomial p, z2 must also be a root for p of x. Great. Now, we use the division algorithm again. We break this down, and we're able to get to saying that q2 of x is able to come out of q1 of x, and it's going to have a degree of 3. By the fundamental theorem of algebra, we're guaranteed that it must have a root z3, and since q2 is contained inside of q1, which is contained inside of p, we know that z3 is once again a root for our initial polynomial that we started with. We then break down q2 of x, we get to q3 of x. q3 of x will now have a degree of 2, because we're stepping down once each time. Since it has a degree greater than 0, we're guaranteed a root there, which is once again going to be a root of our initial polynomial. We break it down once again, we get to q4 of x. It has a degree of 1, so it is guaranteed to have a root of z5. We plug that in, and so that's going to once again be yet another root. And finally, we use the division algorithm one last time, and we get down to q5 of x, which now has a degree of 0. And since we have a degree of 0, we're not able to get a root out of it, so I've used up all of our roots. So we've managed to pull out 5 roots because we start at degree 5, and each step we're able to pull out one root as we subtract by 1. And so we're finally left with some constant polynomial, and that's where our a, the a that multiplies the whole thing, that's going to be our 5th quotient polynomial at the very end. It's going to be a times x minus z1 times x minus z2 times x minus z3 times x minus z4 times x minus z5. Pretty cool. So really, really deep stuff from advanced mathematics that we can actually have a pretty good of understanding just from what we've managed to learn about polynomials so far. Pretty impressive. All right, we'll see you at Educator.com later. Bye.